start with some short introduction. I will explain what is the exact issue with year 2038 problem. I will describe this problem thoroughly, and then I will also give some introduction to gdpc project itself. Afterwards, I will present a solution for this issue. I will give some comments regarding Linux kernel and also how the problem is going to be solved in the gdpc. Afterwards, I will present the most up-to-date development status for gdpc. I will share some hints for people who would like to contribute to gdpc project. I will then close this presentation with some short summary, and hopefully I will give some questions to the audience. So a few words about me. My name is Łukasz Majewski. I'm embedded software engineer employed in DENX Software Engineering. You can reach me with this email. I do have electronic background. I'm involved in several open source projects. Most notably, I'm the device firmware update maintainer in Ubuntu bootloader project. I also do some USB related work there. Moreover, I'm involved with in the gdpc with solving the year 2038 issue. Of course, I'm not the only developer there. There is a group of people who are involved. I also did some network-related work with Zephyr. I do have some experience with Linux kernel, and also I provide some DSPs with Yocto project. So what exactly is the year 2038 problem? It happens when on 32-bit CPUs, I mean by 32-bit CPUs, I mean the ones which are using 32-bit word length. When on those CPUs, time key variable, which is signed int, will overflow. And for 32-bit systems, this will happen on January 19, 2038, 3:14 and 7 seconds UTC. So when the time representation, which is POSIX time representation since the POSIX epoch, will change its value from 0x7 and 7x to 0x1 and 7 zeros. What will happen then? After passing that year 2038 threshold time, I mean 19 January 2038, the time represented on systems will be 13 December 1901. This value is because after the overflow, the time will be large negative value. And when we subtract the POSIX epoch time, which is the 1st of January 1970, then after the subtraction, we will have the 13 December 1901. Why this is problematic? And this is problematic because on 32-bit systems like 32-bit ARM, E386, PowerPC, that time will be wrong. And for those systems, if nothing is done, such issue will be for sure. So all the use cases which demand long time of operational for those devices, like heavy industry, railway, automotive, aerospace, medical, those will be affected. What is important? It is important to say that for 64-bit systems, that problem will not happen. And now I would like to say a few words about glibc. We do have 2 releases per year. The next release, which is 2.54, is scheduled to be released on the beginning of August. glibc is quite old project. It conforms to several standards like single unit specification, POSIX, etc. And what is important is to say that it has many ports. By port, I mean it supports many versions of processors. So for example, we have ARM, we have ET106, PowerPC, etc. This is problematic because when we change something with only one architecture, then we must avoid regression on others. So how it is built in the overall ecosystem for embedded project? First of all, we might have Linux kernel binary, which is prepared to work after year 2038 threshold time or not. And this kernel binary should be in sync with Linux kernel headers, which are used during building the glibc itself. We can use enable kernel flag to pass proper version of Linux kernel, but those headers are also used for the glibc, that it will know internally which kind of features are supported by Linux kernel. For example, for year 2038 issue, when kernel provides proper syscalls, in glibc flag assume time 64 syscalls is defined. So this is important to have the same kernel and the same Linux headers which were used during building the glibc. Also, those headers are used to provide exported systems headers from glibc, and those systems headers will be used by user space programs. Next puzzle are user space programs, which are of course developed by companies or developers. And last part are libraries, which might be already installed in the system. What I would like to emphasize is that mixing those components in a wrong way, at least from the year 2038 bug solving perspective, might cause problems. The system might be broken immediately, but in even worse situation, it will fail after we pass the year 2038 threshold time. So it shall be the company or people shall really pay attention about the update strategy for their systems. Okay, and now I would like to share the information about the solution in Linux kernel. In Linux kernel 5.1, which is quite old now, a new set of syscalls which are supporting providing time in 64-bit variables have been added. So, for example, clock set time is there, and also clock set time 64. Those are new syscalls which have different syscall numbers. This is also problematic from the system security point of view, because those new syscalls, new numbers shall be allowed on such systems. What is important is to say that on the 64-bit machines there is no change, because those machines will use old syscalls like clock set time, and those syscalls already provide time with 64-bit variables. For 32-bit systems, it is important that it will use Linux kernel, which is younger than 5.1, to have the opportunity to use syscalls, which will provide proper time after passing year 2028 threshold date. Otherwise, the gdibc itself will use fallback code to use all the syscalls. Such system will be working correctly until the year 2028 overflow time. So to sum up, Linux kernel is well prepared for the year 2028 issue. Now I'd like to say a few words about ARM port design decisions, which were taken to solve the problem in the gdibc. First of all, the idea was to have new port with 64-bit time variables, but that would impose extra work because two separate ports for the same architecture would need to be maintained. And the same situation would be for E386 or 32-bit PowerPC. With new port, the backward compatibility will be broken because one could mix different binaries which are not compatible to each other. So instead, the approach with gradual conversion has been adopted. This means that the current ARM port will gain support for storing time in 64-bit variables in step-by-step manner. And as a result, the time bit 64 flag will be supported by gdibc. This flag also requires large file support, so it also will require passing file offset bit 64 flag. What is interesting for new 32-bit CPU ports like ARC or RISC-V 32-bit, there was imposed requirement that the minimal supported kernel version for those ports must be younger than 5.1. So this means that those ports are immune to year 2028 back from the outset. I do see three use cases for the GSPs which are going to be built. I do assume that the newest possible gdibc will be used, like 2.34 or newer. And then when you use Linux kernel older than 5.1, then the system will work correctly until the year 2028 threshold date. On the other hand, when you use Linux kernel, which is younger than 5.1, then everything shall be working. The key situation is that when, for some any reason, you compile your program with time bit 64, and then it will be run on gdibc, which is not yet supporting this flag. So you may also encounter issues there. And how the problem has been solved in the gdibc project. In gdibc project, there are many people with server backgrounds, cloud backgrounds, desktop development backgrounds. So for them, the year 2028 is not a real problem, because for many years now they use only 64-bit machines for their work. and it was hard to convince the community that there are some use cases which will demand providing 64-bit time support on machines which use 32-bit word length. Also, we have to convince them that there are some use cases which will require, for example, 20 years lifespan of the product. After that, it was fairly easy, and we received large support from the community. The first step was to refactor the gdibc itself, because up to this point, gdibc was using on 32-bit machines variables, 32-bit variables, which were storing time in variables with 32-bit size. But after the rework, where, for example, struct timespec has become struct _ timespec 64, no matter if we run on 32 or 64-bit port, the time is always represented with 64-bit variables. So this prevents from some AB mismatches for alignment and size mismatches. Because for example, user space program I use struct timespec 64, gdibc will coerce it to timespec, struct timespec, which is smaller, and then use that wrong data to issue some syscall. So this is already converted. Next step was to introduce _ timesize macro. And this macro provides size for default time t for target architecture. This means that by default, the time size defined equals to word size. So for 32-bit ARM processors, it is 32. For 64-bit processors, it is 64. As I have mentioned before, for 32-bit CPUs added now, it is set explicitly to 64. So from the very beginning, they are immune to ERR20 problem. And for ARM, for example, or the other ports which are already available, setting it to 64 would cause backward compatibility breaks. And what is interesting is that in gdibc source code, such problematic architectures which need the conversion, they are not taken port by port, but they are defined as ones which have time size not equal to 64, and in the same time for which word size is equal to 32. Now I would like to present how the redirection is performed in the embedded system and in the gdibc source code. So gdibc exports headers, which then are used by user space program. One such header is the features time 64.h. In that feature, the use time bit 64 flag might be defined, and this flag is defined when somebody compiles with the -d_time bit 64. So what will happen then? Let's consider system exported time.h header. So we, for example, have the get time of day syscall. And as we can see, when the use time bit 64 flag is defined, we have redirection. So get time of day is redirected, the call to get time of day is redirected to _ get time of day 64. So in that way, it is possible to have the proper time handling. And now let's look on the glibc sources itself. So for example, in the time.h internal glibc header, we have declaration for that get time of day 64-bit function. Please pay attention that it also uses the internal representation for time val 64. So it uses time val which members are 64-bit variables. And for systems which are 64-bit systems, we just have simple preprocessor aliasing for get time of day. And now I'd like to say or explain how in the sources two versions of get time of day functions are provided. One is underscore get time of day 64, which simply calls another function which is called get time 64. This function provides 64-bit time, or when the system is not ready to support 64-bit syscalls, it returns, it uses all the syscalls, and in that way can still be used. But what is important is that we use clock get time 64 to fulfill requirement for get time of day 64, and then that 64-bit value for time spec is converted to 64-bit version of time val structure. So this is the main function which is used now in the glibc, and this can be used on systems which are prepared to work with after year 2038 threshold date, or 64-bit systems. And now the second part of the same file, we do have here the fallback code, which is the get time of day. This code is used when the user program is not compiled with the -d time bits 64. As we can see, it uses a 32-bit version of time val, but internally it calls the get time of day 64-bit version of the function, so it calls this function. And then it checks if we have overflow with the seconds value. So this means that when we detect that we have overflow, we do have the overflow for the seconds, then the system which is not prepared to work after year 2028, it will just exit, and the kernel will be set to overflow. In that way, one can discover that the system is broken after passing year 2038 threshold time. If everything is okay, then we convert the 64-bit version of time val to 32 version of time eval. And also we have some aliasing to have get time of day call properly redirected here. So what is the development status for today, up to today? As I have shown, we have two versions of get time of day, for example, which is the one for 64-bit time, and second one is for 32. So all the functions which are exported by glibc and they use time-related structures, they have been already converted to have similar to get time of day structure. And those were around 80 functions, and this is already pulled to the glibc master branch. When the project has started, there were some internal tests to check if we do have proper operation or if we not introduced regression. And those internal tests have been ported to glibc test suite. So they are all now in the glibc test suite, can be used by anybody. And only a few, I think those are 2 or 3 tests are still under discussions. This is getter usage and test access time. Also, the glibc test suite now is supporting allow time setting flag. This flag would allow to adjust the time on system on which we run tests, so we can check how the system will behave after passing the year 2058 threshold date. And this allow time setting flag can be used from glibc test suite to be used, for example, on QEMU-based ARM test board. So this all is already in place. What is even more nice is that we now have the consensus about providing support for time bit 64 flag, which means we will be able to fix the year 2028 problem on 32-bit systems. The consensus is that if everything goes okay, the code shall be pulled for 2.34 release. I do have the information that the compliance team is now testing is going now to test patches which are adding that feature with the Fedora Rawhide, and we are waiting for the final round of review. So if everything goes smooth, then it is a high chance that it will be pulled for the 2.24 release of glibc. Of course, there would be some missing parts, but not many. I think the most important one is the UTMP, because some subsystems need to be fixed anyway, and during that fix, we will provide support for year 2028. So we are heading in a very, very good direction with this feature. And now I would like to discuss a bit how users can test their systems if they are complying with year 2028. First, one can use the CI script, which is built on glibcs. This script for all ports supported, for all architectures supported, it builds binutils, GCC, glibc, and on top of it, it runs glibc tests. Then one can use the meta year 2038, which is Yocto meta layer, which allows you to build the glibc under test and then use that BSP to run QEMU emulated 32-bit ARM board, and then use that board and use the glibc test setup with the allow time setting flag to check or run all the tests which are now in the test suite to check how the system will behave, for example, after passing year 2038 threshold date. Another option is to use the same meta layer, build the board, build your program for this board, and then run it directly on this board with the date set ahead after the year 2038 threshold, and see if you see any problems, if you see overflow errors, etc. More information is in the README under this link. And also there is the ABI compliance tool, like the ABI compliance checker, to see if there is no ABI problem between gdibc releases. One of the requirements from the community to have the code which is fixing year 2038 issue was to have all the time-related functions exported from gdibc covered by unit tests. And now I think we have almost all of them covered. They are pulled to the master repository. For example, we have the tst upjusttime.c test file. Additionally, it was also requested to have the same tests used for testing the code with year 2038 support enabled. So to do that, there is new file introduced, tst upjusttime.64.c, and this test directly includes the test from tst upjusttime, and this particular file is built with -d time bit 64 flag set and file offset bit 64 set. So one test are used with and without year 2038 time support enabled. Of course, the naming convention is the same, like TST and then the rest, but here I only gave the example of TST upjusttime. So if you grab for TST in the gdibc source tree, you will see more tests and more versions regarding year 2038 testing. So what are the future plan for this feature of gdibc? For sure, the 64-bit time on ports which are using 32-bit CPUs is going to be enabled by default. When minimal supported Linux kernel version will be newer than version 5.1. This will not happen soon though, because now gdibc minimal supported Linux kernel is 3.2, so I predict that it will take many years before this will happen. Also, users, developers, companies can validate their programs. We need to validate their programs if they will work after passing year 2038 threshold. Simply they can set the date on the test board and then check if overflow errors will happen. I would like to also mention that the code now is tested with ARM 32-bit board, which is run under QEMU. Although it is possible to build test code for E386 and PowerPC 32-bit, but as up till now, there was no need to provide such test boards for those two architectures. So if there will be interest, then probably such support will be provided. Last but not least, I would like to encourage developers to fill Bugzilla tickets, because in that way gdibc community can know that there are some issues to be fixed, and we can tackle those problems with some structured manner. So if somebody would like to send his patch instead of filling the Bugzilla ticket, now I would like to share some hints for him or her. First of all, before any code is pulled to the repository or it is even review the developer or the company for which he works. It needs to have the license agreement contract signed with Free Software Foundation. Then there is a need to develop the consensus in the community. This means that the developer from the very beginning shall be prepared that community will request some changes, like adding feature or removing feature of his patch, and he shall be prepared to be flexible to reach the consensus. The consensus in the gmhc community is also a very good tool which is preventing trolling. And when the consensus is reached, then it is the responsibility for the developer who prepared that patch to perform CI testing to check if the patch applies, and he or she is pushing the code to the master repository. So this is different than in Linux community, that there is no delay between the end of discussion about the test and the time the code is pulled to the Linux kernel repository. There is no such delay. And now I would like to say a few words regarding, to sum up this presentation. The year 2058 problem, as I have shown before, is a severe threat, at least for some use cases where the device is going to be used for next 20 years. It looks like we do have the 17 years for preparation, but as I have said before, for some use cases it is really short time. If you would like to have the year 2058 compliance now, if it's possible, then please use 64-bit CPU for new project, and in that way you will not have any issue with year 2058. If for any reason you are forced to use 32-bit CPU, then please use timebit 64 flag to compile your program when this flag will be available in the glibc. And also please keep in mind that finally support for 32-bit time for systems with 32-bit CPUs will be dropped in glibc. Of course, this will not happen in really near future, but this also shall be considered. So this is everything I wanted to share, and now I would like to have the discussion or maybe answer some questions from the audience. Thank you very much for your attention.
Thank you very much, Łukasz, for your talk. It's good to hear that we have people that take care of such a problem, even though it might seem that it's still far in the future. But thank you also on behalf of Siemens regarding this regard. Also, Roger made a little remark. Please tell the people writing software for nuclear power plants to take care of the 2038 issue. It's for our kids and this great planet. Yeah. Now we get to the questions. We got one question from Erjan. Do you think we still have many 32-bit systems in 2038? If so, which areas do you envision?
As I said, I can share that I had the case that in some transportation systems, there were requirements 1 year ago that the system shall fulfill or work correctly after setting the date to year 2058. And of course, that device which was used, it was using 32-bit processor. So yes, there are some use cases. 32-bit processors are pervasive because they are with us for many years now. And even some companies, they are promising that some SoCs are going to be produced by them in next 15 years. This means that when somebody develops the system now, at least for 15 years, it will be supplied with that particular SoC. I can imagine that it will be extended easily for at least 2 years, or 3 years, or 5 years, if there is market for that. So in the embedded world, 32-bit processors are pervasive. I can only observe now that maybe there is a little switch to the EMX, 64-bit, let's say, devices. But as far as I'm concerned, still the majority of work is done with the 32-bit processors. Even those are like ARM V5 still.
Okay, thank you. There's another question. Will the missing parts like UTMP conversion make it unusable? Make it unusable? It's good to see it's going in the right direction, but I'm wondering when it's ready to be used in production systems.
I mean, there is, for UTMP, there are patches which are posted to gdipc, and they have the conversion done for this particular part of gdipc, but the committee decided to postpone them as those patches, those subsystems are going to be rewritten anyway because they have their own problems. So if you really would like to use the code, then, for example, my advice is to use 2.34 when the feature is available there, and then apply patches which are required for your system, and then perform the validation. I have shown in my GitHub there is a gdipc repository. There is year 2038 Edge branch, which has all the code in place. So if you are interested, would like to have the system working correctly now, then you can look on this solution, right?
Yeah, thank you. You talked a lot about glibc. Do you know how other systems and projects are dealing with this problem, especially real-time systems? Do you have any insights on that specific topic?
No, I just have the information that Moozle library, it also has been converted, I think, last year to support year 2028 time, but it was done a bit differently than in gdipc. But I do not have any insight about the real-time systems. Sorry.
Okay,